Great. So I want to do a couple of things. I want to do an experiment today. If I can teach without opening my notes, I think it will work. So with it, I think it will. Let's see. So I want to talk about two things today. One, I want to talk about the concavity of entropy. And the other, I want to talk about reversible versus irreversible work. This will be our first time talking about reversible versus irreversible work. We will spend more time into it after our midterm. But today I want to introduce it to you. So let's start with the second one actually, and then we will come back to concavity. Okay, let's start with reversible versus irreversible work. So what's the idea? First law of thermodynamics says du is equal to delta Q plus delta W, right? What does this mean? It means the change in internal energy of a system is equal to the heat given to the system plus work done on the system. Okay, be careful with the signs of everything. In other words, this can be written as minus P external dV if only mechanical work is happening. You could have other sorts of work. You could have chemical work. You could have surface area based work. You could have information work. Next week's statistical physics seminar is by someone who dropped out of grad school at UT Austin and now works in a cryptocurrency company. He started it and he's going to talk about information work. You know, when I'm trying to shove an idea down your throat, I'm doing some work, right? It's not easy. You're resistant. You don't want to learn, or maybe you do. You know, so that is all information work. Also, you can generalize it as some force multiplied by some conjugate variable, right? That's the definition of work, right? What is the driving force and what is the change in that variable? So, but let's just focus on this one. And let's think about a PV diagram where we have a gas at some initial volume VI, okay? And we are interested in taking the gas to some final volume VF, okay? So we have to expand the gas from some initial volume VI to some final volume VF. We can do this in at least two different ways. So the setup here is that you have gas in some container and there is a piston, okay? And the piston will need to be pulled up, right? The piston is maintaining a certain pressure and the gas is at a certain volume. You can do it in two different ways. One is to just pull it suddenly, right? Immediately take the gas to that other volume and expand it. The other is to gradually, very, very slowly pull it, right? So the first one is going to be irreversible because you just pulled it. Gas is like, I don't know what happened. And suddenly it has to take that volume, right? In the second one, you are doing it quasi-statically or reversibly, right? At any stage, the gas is in equilibrium with the piston, okay? At any stage, if you observe, they're really balanced. So, by the way, in this homework, some people already scored 80, don't be sad. There were some silly mistakes. Everyone seems to have the right ideas and one homework will be dropped. Also, there will be enough bonus problems in future homeworks you can make up for what you did. Okay, so but you will start seeing that in future homeworks and midterms the range broadens, and so thermodynamics is deceptive. A lot of you told me it's very easy. It's like, I don't know, the analogy I can think of it is like drinking wine versus drinking whiskey. You know, when you drink whiskey, everything, every little sip, you know, it's hard liquor, right? Wine, you can get deceived. And you can get very drunk on wine too. So thermodynamics is like that. It's very gradual, but it picks up and it adds to become a lot. So we can do reversible work. Reversible work means that P external is equal to P gas at all stages, or irreversible work your graded homework is there, Omar. irreversible work means P external is not equal to P gas. Okay, we just ramped it up. So how will these two processes look like? Process number one is going to look like this. You will be starting from some P final, and you will be coming to some P, sorry, what did I say? You will be starting from some P initial, and you will be coming to some P final, which is equal to P external. Okay, that's reversible work, reversible process when you do the expansion reversibly. You can also do the expansion irreversibly, where you just yanked up the piston all of a sudden. And in that case, it's going to look like this, right? It's like almost a discontinuity. It doesn't matter that initially it was what PI, you just dropped it down to P internal, right? So let's try to calculate the work done in both of these processes. Okay, let's calculate W is equal to integral of delta W for both of these. Okay, so let's do it for irreversible work first, because it's easier. For irreversible work, what can we say? For irreversible work, let's go to the next page. Okay, I will draw the diagram again on next page, and then so we have P, V, we have V initial, we have V final. Irreversible work goes straight from here to here at some P external, and reversible work goes from here to here. There will be a curve, and you can try to find out the equation of this curve by assuming something. If you assume ideal gas, just 1 second, Patrick. So this is P initial, and this is P final. Go ahead.
Yeah, so why doesn't the pressure change in the irreversible case?
In the irreversible, it's like it changed, but all of a sudden it changes, but very quickly. That's the problem. The gas doesn't get time to. The thing to remember in the initial one is literally I have a piston here and I'm very, very slowly picking it up. And then the irreversible one, I just did all of a sudden. Okay.
Why don't we start with this initial pressure in irreversible?
That's not what you experience. You were sitting happily, and I suddenly came and pulled you apart. Do you really still care about the initial pressure at which you were sitting happily? The work did not happen with that. I don't care what pressure you were sitting at. The work happened with this pressure, with this external pressure.
Oh, so it doesn't affect the integral.
No, it's just a little delta point. It doesn't matter. You know, when you multiply it by dV, it just goes away. It was more there. Yeah, go ahead, Sophie.
So when you say it's irreversible, the P external doesn't equal to PS, but in the diagram, it's a straight line where PF is equal.
Yeah, so absolutely correct. So in the reversible work, in the irreversible work, we cannot say anything about P gas, because I mean that is the starting point of thermodynamics, right? We can define state functions. There exist equilibrium states, and we can define state functions for equilibrium states. If you're out of equilibrium, then there is nothing, right? There's what we can. Yeah, go ahead, Amar.
If you do it so fast, doesn't this mean that the system is out of equilibrium?
Yeah, absolutely. But the work expression is still valid. That's the beauty. Right? Good.
So are you saying you shouldn't have drawn a horizontal line at all? It's just
That is not for, good point. This is not for system. This is for the process that is being carried out. Okay. So this P here is generic. Yeah, this is a curve that you have all seen in your physical and chemistry books. Atkins has it, but it skips many of the details. You know, it's a bit subtle as to how you really do it. So, okay, so let's calculate the irreversible work now. So, which is our process two. Process two, which is irreversible. The work done is going to be integral of delta W. And what is delta W? That is minus P external dV. Now P external is a constant, right? We did not change the external pressure. The external pressure is the pressure that it is. So that comes out, and that we are going to write at minus PF integral dV. So that is minus PF VF minus VI. Is this negative or positive? Negative. Does that make sense? This is negative because pressure is always positive, right? Pressure is strictly positive. Does anyone know why? Has anyone done here continuum mechanics? Pressure can never be negative. Force can be negative, but pressure is always negative, positive. It's related to the determinant of a certain matrix. So it's just like it's and modulus of it. But yeah, for now we will just assume pressure is related to the root mean squared of the velocity. So per construction it is positive. So this is negative because PF is always positive and VF minus VI is positive. So the whole thing is negative. So what does this mean? Work done on the system. Work done on the system is negative. What does this mean? It means we were able to actually extract work out of the system. Does that make sense? When gas expands, you get work out of it, right? When steam engine, it's during the expansion process that you get work out of it. If you're compressing, you had to do work on it. So during expansion, you can leave your homework here unless you select it for me. During expansion, work is obtained from the system, right? And what is the magnitude of work that we obtained from the system? The magnitude of the work is PF, I put a modulus sign, PF, VF minus VI, right? This is the amount of work that we were able to obtain by doing the process irreversibly. In this figure, can we color this? This is the area under the rectangle, right? PF multiplied by VF minus VI is nothing but this area, right? So that's the area under the curve. Now let's think about process one, which is happening reversibly. Any questions about the irreversible part? It looks funky, but the basic idea is just pulled it up and got to that pressure. Okay, for the reversible part, once again, W is going to be integral delta W, which is once again minus P external dV, nothing wrong with that. But now it's a reversible process. Okay, so we can do something. We can say this is the same as minus P gas dV or minus P system dV, because during equilibrium, during reversible process, P gas is equal to P external. Okay. What can we do now? Does it help us in any way? How do we proceed further? We have to assume an equation of state. You can do anything here, and I can construct n number of homework and midterm problems and final problems here, right? By giving you complicated equations of state, just the algebra will get complicated. But the idea is the same. If you can connect pressure. Oh, by the way, I forgot to mention one thing. Both of these are happening isothermally at the same temperature. Okay. Temperature is staying constant. Again, I don't have my notes, so maybe that's a bad assumption. We'll see. I think it's an okay assumption. Maybe we don't even need it. In that case, we'll cancel it. So W is equal to minus integral P gas dV. So now let's assume equation of state. Why could we not assume an equation of state in process 2? Go ahead.
Because we don't know anything about P gas.
Because we are not in equilibrium, right? Equilibrium, equation of state applies only to equilibrium. Things, equation of state follows from the fundamental equation, right? And fundamental equation is applicable only to equilibrium. So if you're out of equilibrium, you cannot use PV is equal to nRT. It's wild west, anything is possible. So let's assume equation of state. Let's assume the simplest one here, because we are just for the sake of it. PV is equal to nRT. Okay. So let's call this one as equation 1. Let's call this as equation 2. Let's call ideal gas law as equation 3. Yeah, go ahead.
I didn't understand why we're assuming the equation.
Because otherwise we are stuck. we go home. We can't do anything.
So to find what P for P system, you're just
Yeah,
taking
yeah,
an equation.
yeah,
It could-
yeah.
your
It
point
could be
is
some
taking
other
any
thing.
equation.
Yeah, it could be anything if you wanted. The result that I'm going to prove today is going to be that you get more work if you do it reversibly than doing it irreversibly. I'm going to prove it for ideal gas. After midterm, I'll show you it's true for anything, any process. Reversible work, which is, you know, a lesson for life. If you are in equilibrium, you're more productive. If you're out of equilibrium, things go crazy. So we have this thing. So let's put 3 into, okay, I'll wait for a moment. Let's put equation 3 in equation 2. So what does that give? That gives us W is equal to integral delta W is equal to minus P gas dV, because we are at equilibrium, and PV is equal to nRT, right? So this becomes minus nRT dV by V. And let's assume isothermal. You could derive this even for a non-isothermal process, but just to illustrate my point, let's assume isothermal process. So T is constant. So W is equal to minus nRT. All three can come outside. dV by V, Vi to Vf is equal to minus nRT ln Vf by Vi. How do we denote this thing in this curve, in this figure? What we calculated here is nothing but the area under this one. It's not obvious if you look at the final answer, but if you look at what you did was to write down the equation. We essentially wrote that this curve follows equation of state if reversible, right? And we said that this means we can write P is equal to nRT by V. For example, we just use an ideal gas example over here, but it could be some other gas. So for an ideal gas, you just saw, once again, this work is also going to be negative. W is negative because Vf is more than Vi, right? Yeah, go ahead.
So I'm confused about the initial conditions for the two processes. Are they the same?
The initial conditions are same, but in the, yeah, it's a very good question. So initial conditions are the same. It is just that in the irreversible process, I knocked you, before the process started going in a delta time interval, I knocked you to that other pressure. So the initial condition doesn't matter. The work does happen. Work happens only when you are knocked out of equilibrium. Okay, that's why it is. So if you look mathematically at this, you can see that W is negative. Once again, you are getting work out of the system. This expression on its own, it's hard to see why nRT ln Vf by Vi has anything more than PF Vf minus Vi. You can do it actually. You can do it mathematically also. You will have to assume something about PF. You will have to put in the ideal gas law and you can do it mathematically. So actually, this is a good practice problem for your midterm. And please post solutions online. Otherwise, the practice problems, the purpose is defeated. So let's call it equation number 4. Prove delta W equation 4 is more than modulus of W equation 1. And here you should assume ideal gas in equation 1. Can it be done? I think you can do it. So think about it. But so prove mathematically without using geometric arguments. But geometrically, you can see that the thing that we derived in the process 1 the reversible process is the red part, the area under the red curve, which is more than the green part, the area under the solid green curve, right? So we just showed that, so red area is more than green area in figure on page 2. But therefore, we just showed that reversible work out of a system that you can get out of a system is always more than equal to the irreversible work out of a system. Why did I put equal to? Because the limit of an irreversible process is a reversible process, right? We do it very slowly. We just showed this for an ideal gas. Yeah, just 1 second over. After midterm, we'll show it is actually true for everything. Callan does this discussion. You can go and read it. And this is super important. This is, in a sense, yet another statement of the second law of thermodynamics. Yeah, go ahead.
So if I heard correctly, you said that both processes are carried by the thermic, right? But how can you say that process 1 is isothermal, but the gas at each point is not equilibrium? Is temperature defined at equilibrium?
Yeah, well, that's why I did not use it in the derivation for process 2. We did not use it, right? We did not use that it's isothermal. We had to use it in process 1. So in process 2, we did not have to make use of the fact that temperature is even well defined.
Okay, so we can say that this process is carried by isothermic, right?
Yeah, it's hard to say because it's irreversible. Anytime you are irreversible, you have to be careful. Okay, so maybe you were in mechanical equilibrium, maybe you were out of mechanical equilibrium, but maybe you were in thermal equilibrium. That will be a strange process where somehow you are out of mechanical equilibrium, but thermal equilibrium is perfectly maintained. That's the imagination. And that's why the geometric proof here does not require any of that. But if you try to do it mathematically, you will have to assume that at the end of the process, you reach equilibrium. Yeah, go ahead.
Yeah, so if we're starting at the same states, right, the same P and the same V for both processes, why isn't the area for the irreversible process like a trapezoid?
But that's what Kinjal asked. You started at the same point, kind of. You jumped from here to here, like poop.
Okay.
It doesn't matter that you started from up there. It was just yanked. It's the best scenario I can give for it is like you are in a spaceship, you're having a wonderful time, and all of a sudden the black hole shows up and you get stretched.
But I still don't see how you see that in the diagram because the volume's also changing too instantaneously. Right?
I think this is because this diagram is not like.
You can't even represent that process on the diagram if you have to be very strict about it. This diagram is for intuitive purposes.
So how are you able to
So
connect the rectangle to the irreversible process?
due to this equation is exact. There is nothing wrong about this equation, right? This is just an integral and I'm representing it here. The point to keep in mind is what I wrote here. This is not true for system while this is true for system. Okay, so confusion will happen if you try to think about the lower curve as being true for the system. No, that is for the process, not for the system. Okay.
Okay.
And well, just because you started here, that doesn't mean anything because you got yanked off so quickly. Okay. Any more questions?
The x-axis always represents the external pressure, right?
Yeah, it's just exactly. That's another way of looking at it. X-axis always represents external pressure.
So sorry, the right.
Yes, good point. It's only for the reversible one that it happens to be the system pressure also, right? Good. So there is a practice problem related to calculated work done. Please work on it. There will be problems in the midterm where you calculate it. Okay. I did not spend too much time on calculating this area under curves because that's what to do in PChem. It is a prerequisite for this class. So I could spend 3 weeks just doing that. And I deliberately skipped it because the idea is simple. It's just area under a curve. If you know first law of thermodynamics, you're set. And the things you have to be careful about is it reversible? Is it irreversible, right? That's the first thing. If it's irreversible, you have to use P external. You have to figure out what is the P external. If it's reversible, that is, it's starting to roll on my tongue. But if the process is quasi-static or it is carried out reversibly, then you can use an equation of state. And then you have to think carefully. Is the problem telling me which equation of state to use? Or if it's not saying anything, then you have to say, well, I can't do anything. You haven't given me anything. I'm going to start with equation, ideal gas. But if it's giving you some information, maybe it's saying assume van der Waals behavior or something like that, then you can use another equation of state. Or maybe it is giving you some other equation of state to use. For example, in one of the practice problems, I gave this equation of state, P of V minus B is equal to RT. This almost looks like an ideal gas law. This almost looks like a van der Waals gas. All you are saying here physically is ideal gas assumes point particles with no attractive forces, right? Ideal gas assumes that you are all literally points and you don't talk to each other, right? Which might be true, especially in the Zoom era, that ideal gas approximation was very true, right? No one knew who was in the class. And now what you can do is to start assuming that these are actually spheres of a slight radius, right? But they still don't talk to each other. Their volume is B. And that is the equation of state for this one. Van der Waals says on top of that, that there is some attractive force, and there you get a third term. So that's the equation of state, and that practice problem basically makes you calculate something like this for this other equation of state. It's just algebra, okay? Good. So that was this one topic I wanted to cover today. The other topic I wanted to cover today is quite simple, and you might have guessed it already by looking at the postulates, but we are going to be a bit more quantitative about it, which is the concavity of entropy. What do I mean by that? So we said about one of the postulates that S of E N V in the presence of internal constraints is going to be less than equal to S of E N V, right? Remember, this almost looks abstract at this point, but that was the whole idea. When you have something that is a partition and you remove the partition, the entropy increases. Now,
The second one is for the entropy functionality. The right-hand side.
so you can always, both are at equilibrium, right? Otherwise, we won't be able to define it.
Without internal constraints.
Yeah, this is without constraints, but both are at equilibrium. Otherwise, we wouldn't be talking about entropy. The first one, the idea is that you're summing it up for the individual systems, right? Because one of the postulate tells us that it is additive over individual subsystems, so we can do that business. Why does such a postulate exist? That's something we cannot answer in this class. I don't think anyone knows an answer. That really goes back to the Big Bang, that the universe started in a very, very tiny K, everything collected in one point, and it's going in this direction. In fact, people suspect that this is only true probabilistically if the universe was to hang out for a very, 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 very long time. Then even this would invert, right? But in this cycle that we are in, this seems to be the case. So we cannot prove this, okay? There is something strange about this one. No one can prove the second law of thermodynamics. It exists. There is no known violation. Alex tried to find one, but it did not succeed. He's still trying, I think. Good. So we have this. Now, let me actually use my notes because I prepared it nicely and I will miss out on something important. So, in other words, this tells us that equilibrium state is one at which S E X, and I'm going to call this N and V together as X, okay? All of these non-energy variables. I mean, I could just write NV. Do I gain anything from X? No, I'm not going to call it X, sorry. Let's just use NV, that's fine. Sorry about that. So SENV with internal constraints is maximized. So we have talked about the first derivatives of entropy, right? We wrote down partial S by partial N at constant EV more than 0. We wrote down partial S by partial E at constant NV more than equal to 0, sorry, more than 0. We did not yet talk about the double derivative of entropy, right? And oh yeah. Is that what you were angry about? Or-
No, I'm still at the exact same question. Why is ds over dv, why is that always greater than 0?
Oh, we proved it, no? We gave some intuition for it, you remember?
If we can go over it again.
Yeah, sure. How did we give it? We had the same idea. We had a curve
Okay.
and we had the piston versus paddle thing.
Mhm.
We had something like this, you know, this was the piston work and this was the paddle work in our energy volume process. Send me a message. Go back and look at the notes. If it's still not clear, send me a message on Slack and I will remind you of where exactly.
Okay.
Yeah, yeah, yeah. Yeah.
Can you just excuse, following up on my question, what do you mean that then that equilibrium state? So you say, in other words, the equilibrium state is one at which SE and V, but that's also at equilibrium. Both are at equilibrium.
Yeah, but the internal constraints exist. So one way of looking at equilibrium is to relax all the internal constraints in such a way that the entropy is maximized. It will become clear. Let me go one step further. So yeah, if we did it around second class or third class, if you don't find it, send me a message or someone can remind on Slack where it is. We had the diagram where we proved it. So what do I mean here? Let's look at this thing carefully. So we have, let's imagine a big container. Okay. And this container is split into two parts. The first part, and we are going to parameterize the extent of this split using a lambda variable. So this left part is 1 minus lambda and the right part is lambda. Okay. So this is side 2 and this is side 1. And we will say that the second side has energy lambda multiplied by E2, number lambda multiplied by N2, volume lambda multiplied by V2. And the first side has 1 minus lambda E1, 1 minus lambda E2, 1 minus lambda, oh, and sorry, 1 minus lambda N1 and 1 minus lambda V1. Okay. So I could have just written it without lambda. It would still work what I'm going to do next, but I would have to introduce it later at a point. Lambda is just a bookkeeping thing, right? If lambda is equal to 0 or lambda is equal to 1, that means there is no partition, right? You have just reached, there is only one. So, and now let's think about S of this total thing with internal constraints, right? What I had written on the last page. We can write it down. Why can we write it down? Because individually, both of these two are at equilibrium. They are just not talking to each other. They cannot do anything. They exist at equilibrium, okay? So how do I write this down? The only reason I can write this down is because if two systems are individually at equilibrium, their total entropy is the sum of their entropies, right? This is not trivial why it should be this way. When you do StatMech, you'll see this comes from probabilities, because probability is multiply of independent events and entropy is log of probability. That's one way of looking at it. But here our postulates tells us that entropy is additive. This additive is fundamental to the extensive property also, right? So this, in the presence of internal constraints, is going to be, and now I'm going to write down NVE together as X, okay? Because I'm not going to change it for a while. So let's call it together as X. So S of X in the presence of internal constraints is going to be S of 1 minus lambda x1, where x1 means E1, N1, and V1, right? Or if it's, maybe I will write down the X notation in a bit, otherwise it can become confusing. So this is going to be S1 minus lambda E1, and you will see why I'm writing the X notation. 1 minus lambda N1 is 1 minus lambda V1. But that's for system 1, right? For system 2, it's going to be S of lambda E1, no, lambda E2, lambda N2, lambda V2, right? And instead of writing all this, I've written it all. So let's just ignore the X part. It doesn't help me because then in a moment I'm going to go away from X. Oh, well, sorry. Okay, you can, if you wrote X, let's just scratch it out. So this is true. This is S of NVE in the presence of internal constraints. Now let's remove the internal constraint. Then the systems, and let's call this as equation number, how far did we get? Equation number 5 today. Equation number 5, okay? S of NVE with internal constraints. S of NVE without constraints. What's that going to be? Any ideas? What can we say about N? It's the sum. Why is this sum? Because the total thing is insulated, right? So you mixed it, but the total number is the particles, the chemical reaction is not happening inside here, right? We could have had a chemical reaction, that would be another story. But when you mixed it, N is going to be 1 minus lambda N1 plus lambda N2. Same thing for V, right? The total volume is conserved. That's not going to change. Maybe it's better that I did not use the X notation. 1 minus lambda V1 plus lambda V2 1 minus lambda E1 plus lambda E2, right? This is equation number 6. And why? And this is slightly subtle. Why could we write it this way? Why is this equal sign true? Because total 1 plus 2 is isolated. So second law of thermodynamics says that the right-hand side of equation 5 is going to be smaller than the right-hand side of equation 6. S of NVE in the presence of constraints. By removing constraints, you cannot decrease the entropy, right? By removing constraints, you can only increase the entropy. Right-hand side of equation 5 is smaller than equal to right-hand side of equation 6 per second law. Yeah. We started by talking about it, and then we moved to adiabatic changes. In the first lecture itself, we spoke about constraints. That's how we started, remember? We said things are divided into two things, and then we moved on to adiabatic things, so we forgot about constraints. Now's your reminder. So, let's write this down explicitly. So S of 1 minus lambda N1, 1 minus lambda E1, 1 minus lambda V1. By the way, the concavity part, this won't be on the midterm, okay? So this part will be on midterm 1, but not the concavity part. The reversible, irreversible will definitely be there. Yeah, right.
So by introducing another parameter lambda, so
Are you projecting the two variables or three variables thing?
You'll see what I'm going to do with lambda. You'll see.
So why are you introducing that?
It will become very clear in a moment. Just give me one moment, okay? If it's not clear, then you can tell me again. I still don't like it. Okay, so plus S of lambda. This lambda trick is quite important here. Lambda N2, lambda E2, lambda V2 is less than equal to S of 1 minus lambda N1 plus lambda N2, 1 minus lambda E1 plus lambda E2, 1 minus lambda V1 plus lambda V2. Now, lambda, what should we do with lambda? Any ideas? Anyone who has not answered? Where is Aiden? Aiden, what do you think? What pops to your mind looking at lambda?
I don't know with lambda, but I do know that like the left-hand side would be linear, so back that right-hand side is.
I'm looking for a word that begins with E. Extensive. I can get the lambda out, right? So it becomes, so I will explain how enthusiastic that makes me feel. Extensive, woohoo. So 1 minus lambda S of N1, E1, V1 plus S is extensive, woohoo. S lambda S of N2, V2, E2 is less than equal to, here we can't do the extensive business. It doesn't really help us. We have to dangle the whole thing, right? So S of, and this is where my X notation would have been useful, but that's okay. N1 plus, it will clean up in just a bit, plus lambda N2, 1 minus lambda E1 plus lambda E2, 1 minus lambda V1 plus lambda V2. Okay, this is all cool, but it still looks just like too many symbols, right? Barely chemistry. What is this? Barely math, barely chemistry, no man's zone. So let's, now if you were to call, should I do it? Okay, let's imagine a very specific setup now for this one. Okay, for this thing where we had a partition. Let's imagine that the volume and number are already equilibrated. Okay, energy is the only thing which is out of equilibrium. Let's imagine Vn already equilibrated, only thermal equilibrium is missing. So then how is our container going to look like? We have this thing. What can we say about the volume on the left side? This is where hopefully, Kinjal, you will see the use for lambda. You tell me. No, it's equilibrated, does not mean it will be 1 minus lambda multiplied by B. It won't be equal, because if you make the volume both each side, then the number will have an issue, right? So this is 1 minus lambda V, and this is lambda V. It's just partitioned, right? If it's equilibrated, think about a partition. If the partition, huh?
I do not remove the partition.
The partition exists such that it allows the volume to come in equilibrium. It exists such that the number is also in equilibrium. The only thing that is different is the energy. It is not allowing energy to exchange. Okay. So in this setup, if I now look at equation number 7, that simplifies. What can we do with equation 7 now? The left side will become 1 minus lambda S of E1. Instead of N1, now I just have to write N, right? Instead of V1, I just need to write V plus lambda S of E2 and V is less than equal to S of, now if N1 is the same as N2 and equal to N, what is 1 minus lambda N plus lambda N? That is N, right? So N comma V, and this thing will be 1 minus lambda E1 plus lambda E2. Now something is starting to emerge. N and V are not doing anything, right? So if you think you have a hand up or you're just stretching, go ahead.
Can we talk about chemical and mechanical equilibrium without thermal equilibrium?
It's a thought experiment, sure.
Okay, what about the Wien experiment?
Oh. You would have put Einstein out of business. Thought experiments are important.
Yes.
In real experiment, you could create something, I don't know, it will be very hard.
because
you would
the
create it.
assignments we used to prove chemical and like,
It would be some very bizarre. How many people here actually do experiments? Okay, there are a few. What do you guys think? Can you answer Omar's question? Can you create a boundary which allows mechanical and volume equilibrium, mechanical and number equilibrium, but not thermal equilibrium? It will be very hard, right? And the other way around might have been easier, right? So this is purely thought experiment, but it's a useful thought experiment, okay? Any more questions? Yeah.
I don't know if we're just not thinking about this correctly, but the constraint is a barrier. So when we take that away, entropy has to increase. What if you added constraints? Because we've decided entropy can't increase, but
It's an internal constraint, right? So when you add an internal constraint, the entropy will have to go down, but now you have to be careful who added the internal constraint, where did it come from, and things like that. So it can be a bit trippy. So let's look at this one and write it down. What's my page number? It's page number 6. On the next page, we have just said that 1 minus lambda S of E1 at some volume A, V, and N plus lambda S of E2 at some volume V and N is less than equal to S of 1 minus lambda E1 plus E2 volume and number. If we plot this for S of E at constant NV, so we are plotting S versus E, and let's say this is my value E1, and this is my, and remember the S function is the same, right? The gas is the same. If you had two different gases, that would be another story, but the gas is the same here. And this is E2. So what this means is the S is going to look something like this. We have just proved that S is a concave function of E at constant N and V. You could have done the same thought experiment, not by keeping V and N equilibrated, but by keeping E and N equilibrated, you would get the same thing for V, right? So S individually is a concave function of any of its three variables. What do we mean by this? So we can plot it over here. If this is E1 and this is E2, this line that you can join between these two, this line gives us S lambda defined as 1 minus lambda S of E1 plus lambda S of E2. Does that make sense? It's just a linear combination, right? If you have the entropy S of E1 at this point, and if you have the entropy S of E2 at this point, and you set lambda is equal to 0, then what is S lambda? Lambda is equal to 0 means this thing is 1 and this thing is 0, right? So lambda is equal to 0, S lambda is equal to S of E1, right? Lambda is equal to 1, S lambda is equal to S of E2, right? And in between, you're moving along this line. What this equation is telling you, what this inequality is telling you, that S lambda is less than equal to S of E lambda, where E lambda is defined as this point over here, right? The entropy at that energy is actually going to be higher and lying above, and this is a concave function. We're always above. This is quite beautiful. Okay, it's just a bit of algebra, and you can work through it and see it's not that complicated. Here right now we had so many variables, and we did thought experiments which made Omar groan in pain, you know, and others also joined his groaning. But it's quite simple. You could do the same thing for S as a function of N, S as a function of V, you know. So remember back early in the class, we had said that partial S by partial E is going to be is positive, right? And we had said, well, linear is also positive. This is also positive, but turns out both of these are not allowed. The only one that is allowed is this one for S versus E. What does this mean for E versus, so let me write down the main message here. Therefore, at constant NV, entropy is a concave function of energy. And a lot of people who really understand thermodynamics thinks this is one of the most profound implications of thermodynamics, that entropy is a concave function of energy. What does this mean about energy as a function of, so we can think of entropy as a function of NEV, right? But we can also think of energy as a function of SNV, and then keep constant N and V. What can we say about energy as a function of S? Will it be concave or something else? Convex, right? So this is almost trivial. I encourage you to go read Callan. He comes up with a very complicated mathematical intuitive argument to prove this. Maybe that will make sense to you or not. He does some sort of contradiction. To me, it's obvious, therefore I'm not going to go through that proof. Yeah.
You crossed out the linear dependence. Would it be the case for reversible process?
Sure. You really like your limiting examples, yes. The limit of all concave function is a linear function, right? The limit of all. Sure, I agree. I call this as Lx instead of X. You'll remember. So mathematically, concave functions tend to have lots of wonderful properties. There is an inequality known as Jensen's inequality. Someone remembers what is that? It's very similar. So it becomes useful in statistical mechanics, which means expectation value of a function is, and I always get it wrong, expected value of a function is more than equal to function of the expected value for concave functions. So when we started this class, the first thing I asked you was your favorite math equation, right? And yesterday I just remembered that no one mentioned two of my very favorite math equations. One is Jensen's inequality, that for concave functions, expected value, let me see, maybe I can show it to you here. I don't want probability curves. I just want wiki. Yeah. You see this thing over here. The function of an expected value is less than equal to expected value of the function. In machine learning, in artificial intelligence, nearly 90% of the methods work due to Jensen's inequality, or they would not work. Anytime has anyone here used DALI? You're using Jensen's inequality when you're running DALI. If your Facebook is suggesting you friends, you're using Jensen's inequality. Anything you do, machine learning models work on this, because it turns out that when you're training a machine learning model, the true loss function is actually very hard to calculate, but Jensen's inequality for certain type of things show you can work with this. So that was one inequality I thought we missed. The other one we missed is the triangle inequality, which is actually, I think it can be derived from Jensen's inequality, right? Which says modulus of A plus B is less than modulus of A plus modulus of B. Anyway, so this is a mathematical fact. We will be using it every once in a while. So at this point, we have basically done a lot of things with the entropy. Our postulates showed us its mathematical properties, right? Our postulates told us that it exists for equilibrium. They told us about its monotonicity, about its extensivity. We skipped the third law of thermodynamics, that it goes to zero as energy goes to zero, or, that's essentially a consequence of the ground state in quantum mechanics. I don't care about it. The reason I don't care about it is because most of the time we are interested in ds, right? So I don't care about what is the reference value. I'm interested in change in entropy, but it exists. And in the homework, I've given you marks irrespective of whether you used it or not used it. So when we come back after the midterm, we will pick up from our reversible versus irreversible work. We will start by showing that this concept of reversible work being more than irreversible work is actually true in general for most systems. Then the next thing we are going to do is to think about, so I asked a question on Slack that NVT are not natural variables for entropy, right? We saw that is an issue because NVE are natural variables for entropy. NVT are not natural variables because you have a partial differential equation. Could there exist another state function for which NVT are natural variables? Turns out there is. It's known as the Helmholtz free energy. So for most combinations of natural variables, you can come up with some state function for which they are natural variables. And that's super useful. That means if you're doing an experiment where your control variables are number, volume, and temperature, you will think about certain free energy. So, and this matters practically a lot. And I think a lot of scientists make mistakes on this. You design some battery material, right? And you are interested in looking at the chemical equilibrium inside this battery material. And you say, oh yeah, chemical equilibrium is when the free energy does something. But the first thing you have to ask, which free energy? And we will get into questions like this, right? Which state function, essentially. We haven't talked about free energies yet, but the idea we will learn is that depending on, so if the battery has a membrane that can move back and forth, then the pressure is being equilibrated, right? And the state function that you're interested in will be different from a battery where the volume is fixed, right? So these type of things we will study. And in maybe 2 or 3 weeks, we will finish a lot of math of thermodynamics, then we will move to practical things. We will talk about phase diagrams. I put in a bunch of topics in the last section that will take us time. I don't know how much we will cover. We will talk about chemical equilibrium, phase diagram. We might talk about multi-component systems, how to read phase diagrams for 3-component systems. It's known as a Gibbs triangle, all those sorts of things. And one of the homeworks will be likely a research paper related to thermodynamics in the later stage of the courses, where you will split into teams and you will make presentation on a homework. That homework will have more weight. And it will be some practical paper where you'll be putting all of this to use and see how it really matters. Okay. Any questions about this or the midterm? Yeah.
So when you go from when you put the constraint, remove the constraints and allow the thing to equilibrate at you allow n and b to equilibrate, right? So initially I have my number and the left hand side to be 1 minus lambda and right hand side to be lambda. And when I allow it to equilibrate, I know my chemical potentials will be equal on both sides. So from that, does it follow that n1 equals one where the number will be equals to 1 minus lambda times something and lambda times something, which is constant for both of them.
Yeah. Are you still confused? You want the volume to be equal?
No, I don't want my volume to be equal. I
Then-
know my chemical potentials are equal.
Yes, chemical potential is equal and pressure is equal.
Yeah,
Right.
so how does it follow from that there that or how can I was saying directly that 1 minus from 1 minus lambda n1 and lambda n2 it will go to 1 minus lambda n and 1 lambda n.
What do you think it should be?
I can say directly that the chemical potentials will be equal and the pressures will be equal.
Imagine, forget about E, and imagine this constraint was an imaginary constraint. Okay? If it was in the middle, you could say that the stuff on the left had volume V1 by 2. We are talking about this one, right? If it was in the middle, then you could say stuff on the left had volume V by 2 and the on the right had volume V by 2, right? Now, if this imaginary constraint was over here, doesn't the lambda thing follow automatically?
Yeah.
So coming to equilibrium for volume is the same as having an imaginary constraint, which is not doing anything. That's the way I think of it. Right? So I put it over here. If I put it over here, then this is 3n by 4, and this is n by 4. Because there I really didn't do anything. It's an imaginary constraint. For the purpose of volume and number, your constraint does not exist. That's the way to think about it. Okay, if you go think of equilibrium, you can get confused. Or maybe I misled you there. So from perspective of number and volume, constraint does not exist. It's imaginary. Okay, I'm not doing anything to it. And in fact, if it really bothers you, you could just remove all of this, just ignore it. Don't even care about it. Say, I don't know. I don't want anything to do with my volume and number. What we drew over here, what we derived, the concavity argument, would still hold true, right? If it really bothers you, we didn't even have to do that. For the sake of, and maybe that's the right way to proceed. Okay, but the thing to, because in this diagram, that is the key today for this thing, there is no number and volume, right? It just disappeared. We didn't care about it, right? That's where it comes from. Keep thinking, and if you don't like it, after midterm, we can start from here again. Okay, so no class on Thursday, no class on Tuesday. Please keep asking questions of like, please do the practice problems. I mean, I'm going to give you a midterm problem which is related to the practice problem. How much more explicit do you want me to be? And then you can't discuss. So now is your time to discuss and have a clear answer ready. And if you still don't want to talk about it, but then you don't want an A in this class, okay, fine. As graduate students, you should not care about A. You should know. I wouldn't go as far as saying you should take pride in the number of B's you get. No, that's a bad idea. But don't obsess over getting an A plus or getting an A or A minus. You know, no one will ever ask you about you will get asked about your GPA for NSF graduate research fellowships and DOE fellowships ask you, which is kind of annoying, but your career as a researcher, your grade is the most important thing in your career as a researcher is what you're already doing is to have a conversation with me, right? That's the most important thing. If you can, you know, keep arguing like Kinjal, he's still unhappy. That's important. You know, that's what I want to see. And the midterm is not too hard. It should take around 2 hours, which means it should really take around 3 hours, you know. But if you do the practice problems, it will be easier. The bonus problem is a lot of fun. Try it. Maybe you solve it. It could lead to a paper. It's totally possible. Yeah. And so, yeah. So, and starting Friday morning, there won't be any discussions on Slack. You cannot post anything on general. If you think there is a typo, send me a direct message. I'll look at it and respond. I will be out of the country this weekend, so it might be a bit of lag. I will be in Europe again, so it might in Sicily. So it might take me a bit of time to respond, but I will have internet and stuff, so I will respond. And then next Tuesday also there is no class. Thursday morning you have to send the midterms either on Slack or here. Don't send it too early, and then you find you could do something better and they want to change it. That's fine. If you do that, just delete the previous message. So when I look at my Slack Thursday morning, next Thursday, I can see your final answer, okay? And some of you I already graded and gave it back to you. The others, I will go and grade it right now. I will put it in my mailbox in IPST. If those of you who don't know where my mailbox is, you can ask any of the chemical physics, biophysics student. You can ask Sumin, Vanessa, Vedant, and Omar. They will tell you where it is, okay? Otherwise, enjoy the midterm and see you next Thursday.